Hey guys, what's up? In this video, we're going to be doing some return-oriented programming, or ROP. In return-oriented programming, it's nothing constructive. It's actually a binary exploitation technique, as you guessed, but it's not something that's particularly well emphasized in the Protostar exercises, so I'm including it in that same category, like group of videos. But keep in mind, it's not actually an exercise on Protostar. I'm just doing it because it is an very important technique, very powerful. If you want to learn more about it, the original paper is actually by a guy named Sakam, and it's called Geometry of Innocent Flesh on the Bone, I think. And it's all about how he basically was able to create a Turing-complete basically programming languages just out of bits and pieces of another program and libraries and things like that. We'll be touching a little bit of that in today's exploit. So we're going to be exploiting ROP-C, and I'll just display the program so we can just examine it before we compile it and do all this fancy stuff. So we have a main function down here that takes the argc and argv arguments from the command line, and argv1 is actually used in here. So we have some string here. It's appears to be a global array here, and we set 0, or we set the first element to 0. And then we call vulnerable function with the first argument passed, other than the program name, to main here, and then return 0. So vulnerable function is here. This is, a vulnerable function. It string copies without checking for the bounds here. So we have a buffer that's allocated. So it's not the same thing as a string here. It's different. The buffer, and then a string passes an input here from main. Main calls it with argv1, so essentially it's the argument that we run the program with that gets copied into the buffer. And of course, we're going to overflow that buffer because the programmer did not catch that little thing there. Above here, we have some curious functions. Of course, these are not going to be functions in a real program that you will see. These are just here to help us a little bit. They'll aid us, and from now on I'll be referring to these three functions here: exec string, add bin, and add bash. I'll be referring to these as fat gadgets. And I know I haven't discussed even gadgets, what gadgets mean here, and I guess I can do that now. So basically, in return-oriented programming, the elements that are run, basically the smallest group of instructions, is called a gadget. Gadget is any group of instructions, executable instructions, that first of all is not injected by the attacker, and 2 ends in a return instruction. In this way, we can actually build a sort of a new machine with our what people refer to as the stack pointer as the instruction pointer. So our stack pointer is basically taking away instructions, which really it shouldn't be doing, but in a way it's not breaking any rules because it's not executing things on the stack. And we'll see that when we go ahead and compile this and exploit it. First thing I want to do is show you that I'm not compiling this with ASLR, or with ASLR disabled. ASLR is enabled simply because I don't care about ASLR. ROP doesn't care about ASLR. So we see that it's 2, which means that it's enabled at this point. Another thing is that I'm not going to be doing the no execs. I'm not going to be making the stack executable. Keep in mind, originally we had this flag here, exec stack, right? But now we're not going to include that because we're not going to be executing anything from the stack. It's just a bunch of returns or addresses to return to. It's the code that's actually doing the hard work, the hard pulling here. Then we have, let's just do our C file, and we'll write it like that. So now we see it's compiled, and now we're ready to begin our exploit. So clearly we would like to call these in a way that we can execute bin bash, because that way we can open up a shell. So clearly we have to call add bin first, then we have to call add bash, and finally exec string. Because you see these all add these like little snippets of stuff into the string here, and then system is called on that string. So obviously we have to kind of customize our stack in a way that will actually produce this effect. So let's go take a look at our stack. So this is our stack. It's kind of sketchy, but just bear with it. Our buffer, this one here, is the cyan color here. And so we obviously have to overflow the buffer. And okay, so anything that I write in these boxes is what it's supposed to be there. Okay, the sizes are going to be on the left side, so I'll have like the sizes of each of these. Most of these are going to be 4 because they're just single words in memory, but the buffer won't. And then on the right side, I'm going to be writing what we're going to overwrite with, or pointers to gadgets. So this is our buffer, or what the program thinks is the buffer, or it is the buffer, but yeah. And clearly, this buffer extends to some point. I actually shouldn't have drawn it like this, because I actually don't know how much the buffer is going to go. I don't know that it goes right up flush to EBP. Anyways, this is the saved EBP when vulnerable function is called. And then this is the return address to main. So I'll just put it in there. Again, it's kind of jank, but just stick with it, it's fine. So yeah, buffer, save EBP, then return address to main. Okay, but we don't want it to do that. That's kind of boring. What we're going to do is overflow this buffer. Let's just say we're going to flow it up, put it in red here, with A's. The save EBP is going to be with B's. So we already know that we're going to have 4 bytes of B's, or 4 B's, simply because saved EBP is always 4. The return address to main, we have to be more careful about this, because we don't want it to return to main. We want it to return to add bin to get our little ROP thing started. But before we do that, let's figure out how many A's we have to write. So to do this, we could look at here, and most people will say, it's 100, so it's got to be 100. But that is where the problem is. We can't do that, because compilers, first of all, they create padding, and second, the buffer doesn't always necessarily have to lie flush to the EBP, just because there may actually be something else going on in terms of, well, I mean, padding is one, but it just usually doesn't work out that nicely. So to do this, we have to do GDB, and let's do it on ROP here. Okay, and let's just disassemble the vulnerable function and see what we get. All right. So the thing we have to be paying attention to is the string copy function. Now, string copy, if you know the x86 stack structure, again, the arguments are pushed in reverse order. So string is pushed, the address of string probably is pushed in first, and then buffer is pushed in right before the last one before the call. This is the call to string copy. Our push is located here, so this EDX must contain the address of our buffer. And we see right in the instruction before that, a load effective address of that. So EBP minus hex 6C must be the beginning of the buffer. Okay, perfect. And we know that EBP is going to point to itself, the saved version of itself. So I'm not going to write that. But essentially, we know 6C here. 6C in hexadecimal, so let's see, 6 times 16 is 96. plus 12, which is C, 108 bytes of A's, 4 bytes of B's, then we're right up to the return address, which now we can exploit. Wonderful. So how do we exploit this? Clearly, we want the address of add bin first. So to do this, we can't just run this code because there's some bytes here that are going to be appended just because of the way that this Linux version compiles things. It's kind of weird, but in a way, it's kind of nice. So the way we can do this is let me just disassemble main, and then I'm going to set a breakpoint at the beginning of main. Oops. And then I know how it's going to do it. It's 56, 55, 55, or 56, 48. So it just adds these 5 bytes here, 5, 6, 5, 5, 5. So that's very predictable. And I can run it and see I'm here in main. Notice I didn't supply any arguments, but that's okay, because right now we're just doing it as just gaining some intel here. Add bin. So here's our address of add bin. It's 56, 55, 55, 78. So let's make a recording of that here. Okay, great. So that's add bin. Next thing we want to do after bin. Clearly after bin we're not satisfied. We want more than that. We want add bash. So what's add bash going to be? Well, let's find out. Print add bash. It's here. Okay, perfect. And then after that, obviously we want to execute our string, or else what's the point of all this? So exec string is going to be at this weird address here. Okay, so we've got all of these here. I do not know what happened there, but that's kind of weird. Okay, so we obviously want to write this return address with the address of add bin, because that's what we wanted to call first. But add bin is a little bit picky about what it wants, because add bin, as if we go look at the C function, ooh, what happened there? It actually takes in a parameter called magic, and it compares it to something before it does its magic, you could say. And the value it compares it to is dead beef. So if we go back here, if we add bin here and returns to add bin, the processor is still expecting what the stack to look like a procedure frame. It expects it to be already set up very nicely and have everything intact. In other words, remember, if you recall the stack frame, we must have these things. So all args, and then a return address, right? And then ESP must be pointing here when it enters the frame. And then remember the first instructions. In fact, we can even go look at vulnerable function. There's a push of EBP and then a move EBP to ESP. So there's a push of EBP. So this is essentially the saved EBP we're talking about. And then there's a movement of these pointers here, but we won't worry about that. In other words, we just have to get our arguments and our return address in the right spot. Okay, so our return address should be the address of our next quote-unquote gadget, which is this red box here. But this pink box here, if we're calling add bin there, in order for this to work, it must be equal to dead beef. And so let me go ahead and write that here. Okay. Dead beef. Okay. So what should this one be then? Well, many of you may say, well, just why don't you put in add bash? That's what we need to call next. Let me tell you right now, that doesn't exactly work. So I'm going to go ahead and draw it in just so we can see what happens, or what would happen if we put add bash there. So after add bin is all done, great. Since it's dead beef pushed on here, then great. We have a bin in our string. Great, that's all what we wanted. then it's going to return to add bash. Now recall add bash, when it enters add bash, it also expects the stack to be in a regular frame. In other words, the thing right below it should be its return address, and the thing below that should be its parameters. Now parameters we do not have a problem with. These are non-written right now. But deadbeef is not the return address. For sure it's not the return address. So there's no way that we can put add bash there simply because we cannot create the stack structure needed to properly execute that. So that's out of the question now. We can't put add bash there. So where are we going to put add bash? Well, we will put add bash. The most reasonable place is somewhere below, either here or below. So exactly where we don't know yet, but we need to find a way first of all to how, if we put it here, how are we going to even get there? And then clearly you're thinking, yes, we need to decrement the stack pointer. We need to find some sequence of instructions that will decrement the stack pointer and allow us to execute add bash. And that's exactly what we need to find. So there's a couple of, or sorry, when I say decrement, of course, I mean reduce the stack. I don't actually mean decrement the pointer. So in effect, I'm saying increment the pointer because lower is higher in this case. Lower is more, or is higher address, and the stack goes up. So there are a couple of instructions that will allow us to do this. We either have increment stack pointer by a certain amount, or we can pop. These two instructions, and then obviously at the end we need a return to make it an actual gadget. So a pop here is actually a great thing, because if we just have one pop, imagine the gadget runs here. If we can find a gadget that basically does pop into whatever register, we don't care, and then a return, what will happen, let's trace this. So when add bin is in here, at the end of add bin, just before it returns, quote unquote returns, the stack pointer will be pointing right here, right? Because add bin was here, yeah, so it will be pointing here. Now, when it does return, the stack pointer is obviously going to move down here, and it's going to execute the instructions pop and then return. Now, pop will push, or will get this deadbeef value into the register that we specify, some register, and then obviously that will decrement this, or increment, sorry, I keep on saying decrement, I really mean increment. Increment the stack pointer to here, and then return will basically call the function that's in this kind of golden box here. So that's what will happen. And this is basically going to be our exploit. And the question is if we can find such a gadget. Now, according to Sakam, this is very likely. Since x86 is so dense, it is almost certain that we'll find something that we need. So let's put his theory to the test, and let's go and, well, first I gotta start this up again. Let's go see if we can find anything like this. So the way I'll do this is by examining 128 bytes of memory starting at the beginning of main, which is here. Wow, so there's a lot of stuff here. How are we going to find what we need? There's a search thing here, which is very nice. And we're going to be very open-minded and just search for C3. Alright, cool, we already hit one. Is this the one we want? Well, this is not very promising, because it looks like the one in here is in main. We don't really care for ones in main, because this one here actually just corresponds to this one here. And usually the closing instructions and functions are not particularly useful. As you can see here, it's not good. We don't really want to change our stack pointer in any way, because then we'll have to change ECX and that's gonna become really complicated. Let's look for the next one. Well, we see here we have a C3 preceded by an 81, preceded by an FF, and then we go over here, preceded by an FF, and then an FD and A7. So to see if this is actually good stuff, we can put it in the disassembler here. So let's see, let's go to FD, FF, A1, C3. We'll disassemble that. Ooh, yeah, this is not going to work. None of this stuff will push. I don't even know what STD is an instruction for in x86, and we have a bad byte there, and just byte definition is clearly not going to do our job. Let's look for the next one. All right, so our C3 here preceded by FD, preceded by, or sorry, 5D, preceded by 5F, preceded by 5E, preceded by 5B. So let's put those in the disassembler and see what we get. Okay, and a C3 there. Disassemble that. Oh boy, yeah, all of these are pops. Really though, we just came asking for one, but we just got a bunch of pops here. So let's take advantage of this one here. So the one just before the return, the address of that is F8, F9, FA, FB. So this is 56, 55, 56 FB. So let's go ahead and write down the address of this. And just for documentation purposes, this is a pop EDI here. So we'll make sure to make note of that. Oh, sorry, that's a 5D. I put it in wrong. So actually we're looking at pop EBP. Yep, so this is EBP. And the address of this is 56, 55, 56, I think, FB, I think. Okay, so now we have that going there, dead beef. All right, so we're actually getting somewhere. Of course, we said, just as promised, that the next one here will go up to our add bash. Okay, and add bash, we're gonna need a couple more boxes here. Apologize for my boxes here. Add bash is also going to need a normal stack layout, and by that I mean, of course, our next gadget address has to be placed right below it, and then below that are our parameters. Now in x86 we know once again that parameters are pushed in opposite order, so Magic 1 and Magic 2, Magic 1 will be pushed last. Will be pushed by the previous. All the things I'm saying are just, quote unquote, so it's kind of hard for me to, actually describe this. But in other words, we want basically Cafe Babe here to be above Bad Food, because Bad Food is pushed basically first. So Cafe Babe goes here. If I can somehow type that, that'd be better. So Cafe Babe. The next one here is Oh Bad Food. So just like that. All right. And then the return address of this, well, I mean, this time it's pretty clear what we're going to do. I mean, we're just going to make this exec string. All right, so this is our exploit. To actually see if this works, let's go ahead and do our little script here. So we're going to vim a ROP exploit Python script. Okay, so we want to fill buff. And that's going to be A times 108, remember, plus B to overwrite the function pointer times 4. Or not function pointer, my bad, the base pointer, the frame pointer, whatever. Then what we want to do is place the value of our first gadget, our big fat gadget, at bin 78, 55, 55, 56 in Little Indian. Okay, after that we want to put in our pop return gadget, which is at FB 56, 55, 56. I'll put that down here. Oh, FB 6, 5, 6. All right, after that, we want to do our dead beef parameter here in Little Indian. That's FBAD. Okay. After that one, after dead beef, we want add bash C5 55 55 56. Oops. C5 55 55 56. And then after that, we want our exec string 4D 55 55 56. Okay, and we want the two parameters cafe babe and bad food. And put that down here. Okay, and bash magic 1. So I believe that's right. Okay, so these are all our gadgets, essentially. Not gadgets, the magics, they are not. But, okay, our payload is just going to be the concatenation of everything. Fill buffer. Then we want to do our add bin. Then remember it's the pop return gadget. Then we want add bin magic. Then we want our add bash. Or, yeah, add bash. Then we want our exec string gadget. Then we want our add bash magic 2. Then we want our add bash magic 1. And then we'll just print that. Because we'll be writing this into an exploit file. Okay. Right, now the moment of truth, we'll go into GDB, drop, and then we will set a disassemble of exec string. So the reason why I'm doing this with GDB is because it just simply does not work if you try to do it in the thing, because if you just run bin bash, it's not going to keep the pipe open. So I'm just doing this in GDB just because it works. Or hopefully it'll work. So let's break right after the system call here, which remember it's 56, 55, 5, 5, 6F. So we're going to stop right after this here. And then we're going to run, this time with exploit. Oh, and we did not get anything, so that means we have some problem. Actually, no, this is correct behavior. We got a shell here in the middle of our GDB. So let's look at our file names. Who am I? I'm obviously Kyle, of course. I can get my IDs and all that stuff. Great. So what happens when we exit this? Well, we hit a breakpoint, which means that our exploit worked because this shell was spawned inside of our GDB, which means that our ROP exploit was successful. All right, so in a nutshell, that is return-oriented programming. So basically, we were able to execute bin bash inside GDB without ever having to inject any of our own shellcode or anything like that, or take advantage of our buffer. In fact, if this buffer were a lot smaller, we would still be able to do it. ASLR was enabled. Our stack was non-executable. So the only thing that we just had to ensure was that we could overwrite this buffer here. That's the only thing we had to ensure with this exploit. So yeah, that's it for return-oriented programming. So thanks for watching. Ooh, I ran out of disk space. And I hope you enjoyed. I hope this is a little bit of a refresher from the Protostar exercises. So yeah, see what gadgets you can find. Take care, and I'll see you in the next exploits.